Welcome! In this session, we will explore problem number 1090, largest values from labels. This is a fascinating problem that combines optimization and constraint satisfaction. We'll break it down step by step, analyze the approach, and understand how to solve it efficiently. Let's get started. The problem involves selecting items from two integer arrays, values and labels. Each item has a value, defined by the values array, and a corresponding label, defined by the labels array. The goal is to choose a subset of these items such that the total number of items in the subset is no more than number wanted, and the number of items with the same label does not exceed use limit. The key objective is to maximize the sum of the values of the chosen items. This means we need to carefully balance the constraints of the subset size and label usage while trying to achieve the highest possible sum. Ultimately, the function will return this maximum possible sum as an integer. Now, let's look at the input and output format. The input consists of the two arrays, values and labels, which are of equal length. Each element in values represents the value of a specific item, while the corresponding element in labels represents its label. Additionally, two integers are given, number wanted, which limits the total number of items that can be chosen, and use limit, which restricts how many items with the same label can be included in our subset. The output is simply an integer that represents the maximum sum of values we can achieve while adhering to these constraints. Let's explore some examples to understand this further. In the first example, we have values as 5, 4, 3, 2, 1, labels as 1, 1, 2, 2, 3, number wanted equal to 3, and use limit equal to 1. This means we can select at most 3 items in total, and for each label, we can only include one item. The optimal subset here is 5, 3, 1. These values correspond to labels 1, 2, 3, ensuring that the label constraint is met. The sum of this subset is 5 plus 3 plus 1, which equals 9. Therefore, the output in this case is 9. In the second example, the values array is 5, 4, 3, 2, 1, and labels is 1, 3, 3, 3, 2. The constraints are number wanted equals 3 and use limit equals 2. This means we can pick up to 3 items, and for each label, we can include at most 2 items. The optimal subset in this case is 5, 4, 3. This selection includes 2 items with label 3 and 1 item with label 1, which satisfies the use limit constraint for label 3. The sum of the values in this subset is 5 plus 4 plus 3, giving us a total of 12. Thus, the output here is 12. In the third example, we have values as 9, 8, 8, 7, 6, and labels as 0, 0, 0, 1, 1. With number wanted equals 3 and use limit equals 1, we can select up to 3 items in total, but only 1 item per label. The best subset in this case is 9, 7, which includes items with labels 0 and 1, each chosen once. This ensures the use limit constraint is satisfied. The sum of these values is 9 plus 7, which equals 16. Therefore, the output for this example is 16. When solving this problem, there are several constraints and edge cases to consider. First, the lengths of values and labels are always equal, and both arrays can have up to 20,000 elements. Each value and label is non-negative and bounded by 20,000. Additionally, the constraints on number wanted and use limit ensure that they are at least 1 and at most the length of the arrays. Some key edge cases include handling single-element arrays, where the solution should return the single value if the constraints allow it. Another case involves arrays with all items having the same label, which tests whether the use limit is enforced correctly. Scenarios where number wanted or use limit equals 1 require careful selection to maximize the result. Lastly, the function must handle large inputs efficiently, even when the constraints are at their maximum, and properly resolve ties when items have the same value but different labels. To solve this problem, we need to maximize the sum of selected values while adhering to 2 key constraints. The number of items chosen must not exceed the specified limit, number wanted, and the frequency of any given label in the subset must not surpass use limit. This requires us to carefully balance value maximization with constraint enforcement. One potential approach is using brute force. Here, we would generate all possible subsets of items, calculate their total values, and verify whether each subset meets the constraints. From the valid subsets, we would return the one with the highest total value. While this method is conceptually straightforward, it's computationally expensive due to the sheer number of subsets we'd need to evaluate, especially with larger inputs. The brute force approach involves generating every possible subset, which has a time complexity of O(2 to the power of n). For each subset, verifying the constraints such as checking label usage and the number of selected items takes O(n). This results in an overall complexity of O(2 to the power of n*n, which is impractical for the input sizes allowed by the problem, where n can go up to 20,000. Instead, a more efficient method is the greedy approach based on sorting the items by their values. Here, the idea is to focus on the highest value items first. By iterating through the sorted list, we can greedily pick items while ensuring the constraints are met. To enforce the use limit restriction, we use a hash map to track how many times each label has been included in the subset. This allows us to efficiently maximize the total value without violating the given constraints. The greedy approach can be broken down into a series of well-defined steps. First, we pair each value with its corresponding label, creating a list of tuples. Next, we sort this list in descending order of values to ensure that the highest value items are considered first. We then initialize a count map to track the frequency of each label in our subset, along with a counter for the total number of selected items. As we iterate through the sorted list, we add items to the subset only if the label's count is within the use limit and the total number of selected items is still less than number wanted. Once either of these conditions is no longer met, we stop the process. This approach is efficient because sorting the items takes O(n log n, while iterating through the list only requires O(n), resulting in an overall time complexity of O(n log n). By prioritizing high-value items, we ensure that the solution is both effective and efficient. An alternative optimization to the greedy approach involves using a max heap. The intuition here is similar to sorting, as we still aim to process the highest value items first. However, by using a heap, we can extract the maximum value more dynamically. The steps include building a max heap of items based on their values, initializing a label count map, and then repeatedly popping items from the heap. Items are added to the subset only if they satisfy the constraints on label frequency and the total number of selected items. The process stops once number wanted items have been selected or the heap becomes empty. The complexity of this method involves O(n) for heap construction and O(n log n) for extracting items, which matches the sorting-based approach in overall time complexity. However, the heap-based method is less intuitive and harder to implement, with no significant advantages over sorting for this specific problem. The sorting-based greedy approach is the strategy of choice for this problem. It is straightforward to implement, easy to understand, and achieves an optimal time complexity of O(n log n). By sorting the items by value in descending order, we ensure that the highest value items are prioritized. The use of a label count map allows us to efficiently enforce the use limit constraint, while the iteration process ensures that no more than number wanted items are selected. This approach effectively balances greediness with constraint management. A key insight is that sorting the items simplifies the problem, as it guarantees that the highest value items are always considered first. While the brute force method explores all possible subsets, it is computationally infeasible. Similarly, heap-based solutions offer no clear advantage over sorting. The greedy approach strikes the perfect balance between simplicity and efficiency. The final complexity of the chosen approach is as follows. The time complexity is O(n log n), which comes from the sorting step, and the space complexity is O(n), required for storing the sorted items in the label count map. This combination of time and space efficiency makes the sorting-based greedy approach ideal for handling the constraints of this problem. By leveraging sorting to prioritize high-value items and using a simple rule-based system to enforce constraints, this method achieves the goal of maximizing the total value while respecting the given limits. It is both elegant and practical, providing an optimal solution within the problem's constraints. In this problem, we are tasked with selecting a subset of items from two given arrays, values and labels, while adhering to three constraints. First, we aim to maximize the sum of the values in the subset. Second, the total number of items in the subset should not exceed the limit defined by number wanted. Lastly, each unique label can appear in the subset no more than use limit times. To solve this, we break the problem into a series of methodical steps. Initially, we pair each value with its corresponding label to create a list of tuples, allowing us to handle both attributes efficiently. For example, if values equals 9, 8, 8, 6, and labels equals 0, 0, 1, 1, the resulting list of pairs would be 9, 0, 8, 0, 8, 1, 6, 1. Next, we sort these pairs in descending order based on the values. This ensures that the items with the highest value are considered first when constructing the subset. In our example, the sorted list remains 9, 0, 8, 0, 8, 1, 6, 1, since it is already in descending order. Sorting allows us to prioritize items that contribute the most to the total value, which is crucial for maximizing the sum under the given constraints. After sorting the pairs, we set up the tools needed to enforce the constraints. A dictionary called labelCount is used to track how many times each label has been added to the subset. For instance, if label 0 has been used once and label 1 twice, the dictionary would look like 0, 1, 1, 2. We also initialize selected count to 0, which keeps track of the total number of items in the subset. Similarly, max value sum is initialized to 0 to accumulate the sum of the selected values. With these in place, we iterate through the sorted list of pairs. For each pair, value, label, we verify whether adding it to the subset would violate the constraints. Specifically, we check that the total number of selected items does not exceed number wanted and that the label's usage does not go beyond use limit. If both conditions are satisfied, we add the value to max value sum, increase selected count by 1, and update label count for the current label. If any constraint is violated, we skip the current pair. To optimize performance, we can terminate the iteration early if selected count reaches number wanted, as no additional items can be added to the subset. Once the iteration over the sorted pairs is complete, or the subset size limit has been reached, we return max value sum as the final result. This value represents the maximum sum we can achieve while respecting the constraints on both the total number of items and the frequency of labels. There are several key insights into why this algorithm works effectively. First, sorting the pairs by value ensures that we always prioritize higher value items, which is essential for maximizing the sum. Second, the greedy approach of iterating through the sorted list and selecting items only when constraints are satisfied allows us to efficiently balance maximizing the value with adhering to the rules. Third, the ability to terminate the loop early when the subset size limit is reached avoids unnecessary computations. Finally, the use of a dictionary for tracking label counts ensures that constraint checks and updates are both fast and efficient. Together, these elements create a robust and optimal solution to the problem. To implement this algorithm efficiently, we rely on two primary data structures. The first is a list of tuples, referred to as pairs, which stores the value, label, combinations. This structure makes it easy to sort the items by value and access both the value and label for each item. Sorting the list of n pairs requires n log n time. The second key data structure is a dictionary called labelCount, which keeps track of the frequency of each label in the subset. For example, if label count equals 0, 1, 1, 2, it means that label 0 has been used once and label 1 has been used twice. Dictionary operations, such as updating the count or checking the frequency of a label, are performed in O(1) time on average. Combining these structures with the algorithm steps gives us a total complexity of n log n for sorting the pairs and n for iterating through them, resulting in an overall time complexity of approximately n log n. This ensures that the solution remains scalable even for larger inputs. While the algorithm is robust, it's important to consider edge cases to ensure correctness in all scenarios. One edge case is when no items can be selected. This could happen if all labels exceed use limit or if number wanted is set to 0. In such cases, the algorithm should return 0 as no items are eligible for inclusion. Another edge case occurs when all items have the same label. Here, we can only select up to use limit items with that label, even if the total number of items is less than number wanted. For instance, if use limit equals 2 and all items share the same label, only the two highest value items can be chosen. A third edge case is when the subset size limit, number wanted, exceeds the total number of items available. In this situation, the algorithm selects all items that satisfy the use limit constraint, as the subset size limit is not restrictive. These considerations ensure that the algorithm handles a wide range of inputs gracefully and produces the correct result in every case. Let's walk through an example to see the algorithm in action. Suppose the input consists of values equals 9, 8, 8, 6, labels equals 0, 0, 1, 1, number wanted equals 3, and use limit equals 1. First, we pair the values with their labels, resulting in pairs equals 9, 0, 8, 0, 8, 1, 6, 1. We then sort these pairs in descending order by value, which keeps the list as 9, 0, 8, 0, 8, 1, 6, 1. Next, we initialize the constraints, label count equals, selected count equals 0, and max value sum equals 0. As we iterate over the sorted pairs, we first select 9, 0, adding 9 to max value sum, updating label count to 0, 1, and incrementing selected count to 1. The next pair, 8, 0, is skipped because label 0 exceeds its use limit. We then select 8, 1, adding 8 to max value sum, updating label count to 0, 1, 1, 1, and incrementing selected count to 2. Finally, 6, 1, is skipped as label 1 exceeds its use limit. The iteration stops, and we return max value sum equals 17 as the result. This Python solution for LeetCode problem number 1090, largest values from labels, begins by pairing values with labels and sorting these pairs in descending order of values. This ensures that the highest value items are considered first. A dictionary, label_count, is used to track how many times each label appears in the selected subset. The total underscore value variable accumulates the sum of selected values, while selected_count tracks how many items have been chosen so far. The function iterates through the sorted list of value label pairs. For each pair, it checks two conditions: whether the total selected count is less than the allowed number wanted and whether the count of the current label in the subset is within the use limit. If both conditions are satisfied, the item's value is added to the total, the label count is updated, and the selected count is increment. The loop exits early if selected_count reaches number wanted to optimize performance. The function ultimately returns the total underscore value, which represents the maximum possible sum of values while adhering to the constraints. This efficient approach ensures that the problem's requirements are met, making it suitable for large inputs within the given constraints. Here, we start by pairing the values with their respective labels. Each value label pair is stored as an array in a list called paired. After populating this list, we sort it in descending order based on the values. This ensures we prioritize the highest values first when making selections. Next, we initialize a hash map called labelCount to keep track of the number of times each label is used in the selected subset. We also set up two variables: total value, which will store the sum of the values we select, and selected count, which keeps track of the number of items we've chosen so far. Now, we iterate through the sorted list of value label pairs. For each pair, we extract the value and label. We then check two conditions: whether the total number of selected items is still below the allowed limit, and whether the current label's usage count is within the specified use limit. If both conditions are met, we add the value to our total, update the label count in the hash map, and increment the selected item count. If selecting an item causes the total number of selected items to reach the maximum allowed, we stop the process immediately using a break statement. This ensures we don't perform unnecessary iterations once our constraints are satisfied. Finally, after the loop finishes or is terminated early, we return the accumulated total value, which represents the sum of the largest values we could select while respecting the constraints on the number of items and the usage limits for each label. To solve this problem, we start with the given input, values, labels, number wanted, and use limit. First, we pair each value with its corresponding label and sort these pairs in descending order based on the values. This gives us the ordered list: paired equals 5, 1, 4, 1, 3, 2, 2, 2, 1, 3. Next, we initialize a dictionary called label_count to keep track of how many times each label has been used, a variable total_value to store the sum of selected values, and selected_count to count the number of items chosen. Now, we iterate over each pair in the sorted list. For the first pair, 5, 1, the conditions are met since selected_count is less than number wanted, and label_count for label 1 is less than use limit. We add 5 to total underscore value, update label underscore count to 1, 1, and increment selected underscore count to 1. For the second pair, 4, 1, the condition fails because label underscore count for label 1 has already reached the use limit of 1, so we skip it. Moving to the third pair, 3, 2, the conditions are satisfied again, so we add 3 to total underscore value, making it 8, update label underscore count to 1, 1, 2, 1, and increment selected underscore count to 2. The fourth pair, 2, 2, is skipped as label underscore count for label 2 has hit the use limit. Finally, for the fifth pair, 1, 3, all conditions are met, so we add 1 to total underscore value, resulting in 9, update label underscore count to 1, 1, 2, 1, 3, 1, and increment selected underscore count to 3. At this point, we have selected the maximum possible items while adhering to the constraints. The output for this example is total underscore value equals 9. Now, consider a second example where we increased the use limit to 2. The input values are 9, 8, 8, 7, 6, labels are 0, 0, 1, 1, 2, number wanted is 4, and use limit is 2. As before, we start by pairing and sorting values with labels, resulting in the ordered list, paired equals 9, 0, 8, 0, 8, 1, 7, 1, 6, 2. We initialize label underscore count as an empty dictionary, total underscore value as 0, and selected underscore count as 0. In the first iteration, the pair 9, 0 meets the conditions, so we add 9 to total underscore value, update label underscore count to 0, 1, and increment selected underscore count to 1. For the second pair, 8, 0, the conditions are still valid since label underscore count for label 0 is less than the use limit of 2. We add 8 to total underscore value, now 17, update label underscore count to 0, 2, and increment selected underscore count to 2. The third pair, 8, 1, also meets the conditions, so we add 8 to total underscore value, making it 25, update label underscore count to 0, 2, 1, 1, and increment selected underscore count to 3. For the fourth pair, 7, 1, the conditions are satisfied again, so we add 7 to total underscore value, resulting in 32, update label underscore count to 0, 2, 1, 2, and increment selected underscore count to 4. At this point, we have selected 4 items, which is equal to number wanted, so we stop. The fifth pair, 6, 2, is not considered. The total underscore value for this example is 32. Now, if we adjust the constraints further, let's examine a case with limited selection. In this third example, the input values are 10, 9, 8, 7, labels are 2, 2, 2, 2, number wanted is 2, and use limit is 1. Pairing and sorting the values with labels gives us the ordered list, paired equals 10, 2, 9, 2, 8, 2, 7, 2. We initialize label underscore count as an empty dictionary, total underscore value as 0, and selected underscore count as 0. Starting with the first pair, 10, 2, the conditions are met since selected underscore count is less than number wanted and label underscore count for label 2 is less than the use limit of 1. We add 10 to total underscore value, update label underscore count to 2, 1, and increment selected underscore count to 1. For the second pair, 9, 2, the condition fails because label underscore count for label 2 has already reached the use limit, so we skip it. The third pair, 8, 2, is also skipped for the same reason, as is the fourth pair, 7, 2. With no additional items meeting the criteria, we conclude with a total underscore value of 10. This demonstrates how the constraints on use limit can significantly restrict the selection process, even when high-value items are available. To analyze the time complexity of our solution, let's break it into its main components. First, we pair the values and labels lists using the zip function. This operation has a time complexity of O, n, where n is the number of elements in the input lists. Once paired, we sort this list of tuples in descending order based on the values. Sorting a list of size n uses an efficient algorithm like timsort, which has a time complexity of O, n log n. Next, we iterate through the sorted list to select items based on the constraints. In the worst case, this involves processing all n elements, which is an O, n, operation. During each iteration, we check 2 constraints, whether the total selected items are less than number wanted and whether the label count is within use limit. These checks are constant time operations, O1, as they involve basic arithmetic and dictionary lookups. Since the sorting step dominates at O, n log n, the overall time complexity of the algorithm is O, n log n. The space complexity of the solution can also be broken down into its components. First, we store the paired list, which contains n tuples, each representing a value and its corresponding label. This requires O, n, space. Next, we use a dictionary, label_count, to keep track of how many times each label has been used. In the worst case, where all labels are unique, the dictionary will store n entries, consuming O, n, space. Additionally, the sorting operation may require auxiliary space. For Python's timsort algorithm, this auxiliary space is O, n, in the worst case. When we combine these, the dominant factors are the space used by the paired list and the dictionary, both of which scale linearly with the input size. The auxiliary space from sorting does not change the overall asymptotic complexity. Therefore, the total space complexity of the solution is O, n. Now, let's consider the best, average, and worst cases for this algorithm. In the best case scenario, the algorithm might terminate early if the selected _count reaches number wanted before all elements are processed. However, since the sorting step is always required, the time complexity remains O, n log n, regardless. In the average case, the algorithm processes a significant portion of the sorted list, and the time complexity similarly stays at O, n log n. In the worst case scenario, all n elements need to be processed, which occurs when all labels are unique and the use limit is large enough to allow maximum selections. Even in this case, the sorting step dominates, ensuring the time complexity is O, n log n. Across all cases, the sorting step is the most computationally expensive part of the algorithm, defining its overall complexity. Comparing this solution to a brute force approach highlights its efficiency. A brute force method would involve generating all possible subsets of the input values and checking which ones satisfy the constraints. With n elements, there are 2 to the power of n possible subsets, leading to an exponential time complexity. On top of that, verifying each subset against the constraints would add more computational overhead, making this approach infeasible for larger inputs. In contrast, our solution uses sorting and a greedy selection process to efficiently maximize the sum while respecting the constraints. This reduces the time complexity from exponential O, 2 to the power of n, to O, n log n. Mathematically, sorting the list contributes O, n log n, while iterating through it adds O, n. Since O, n log n, dominates, the total time complexity is O, n log n. For space, the paired list and the label_count dictionary require O, n, space, and sorting adds O, n, auxiliary space. Combining these, the overall space complexity is O, n. When solving this problem, there are a few common mistakes to watch out for. First, it's easy to overlook the use limit constraints. If you simply select items based on their values without checking how many times each label can be used, your solution can quickly become invalid. For example, even if you pick the highest value items, exceeding the allowed count for any label breaks the rules. Next, sorting incorrectly can also lead to issues. The focus should always be on maximizing the sum of values, so sorting based on labels first instead of values can give you a suboptimal result. Lastly, don't forget about the number wanted constraint. Picking more items than allowed might satisfy the use limit but would still violate the problem requirements. Always ensure the selected subset meets both conditions simultaneously. Another pitfall to avoid is implementing your solution inefficiently. Using nested loops or redundant checks when filtering items by labels can significantly increase the time complexity, which becomes problematic for larger inputs. Aim for a clean and efficient approach to handle constraints without unnecessary overhead. Additionally, skipping edge cases can lead to missed errors. Scenarios like number wanted equals 0, use limit equals 1, or when all items have the same label often reveal hidden flaws in your logic. These edge cases may not occur in standard test inputs, but they are crucial for ensuring your solution is robust and handles all possible inputs correctly. To perform well in interviews, it's important to focus on key insights for this problem. First, always sort the values array in descending order while keeping the mapping to their labels. Greedy strategies work best when starting from the highest value and working downward. Next, use a dictionary or hash map to efficiently track the count of each label. This ensures you can enforce the use limit constraint without repeatedly scanning the list. Additionally, think of this problem as a variation of the constrained knapsack problem. While it's not exactly the same, the label limits and item count restrictions add layers of complexity that test your ability to manage multiple conditions. Finally, be prepared to clearly explain your reasoning during interviews. Whether it's how you decided to sort or how you're tracking constraints, clear communication is key. If you want to explore related problems, look at LeetCode 1046, which also uses greedy principles, or LeetCode 1094, which involves managing limits within constraints. There are alternative approaches to solving this problem, each with its own trade-offs. A brute force approach would involve generating all possible subsets, filtering those that meet the constraints, and calculating the sum for each. While this guarantees correctness, its 2 to the power of n time complexity makes it completely impractical for large inputs. A more efficient method is the greedy approach with sorting. By sorting items by value first and iterating through them while enforcing the number wanted and use limit constraints, you can achieve a solution with n log n complexity. However, this approach requires careful implementation to ensure all constraints are respected. Another option is to use a max heap or priority queue. By always selecting the highest value item while enforcing constraints, you can achieve similar efficiency. This heuristic approach may be slightly more complex to implement but can perform better for certain types of inputs. Each method has its strengths, so choose the one that best matches the problem requirements and constraints. Great job! We've covered problem number 1090, breaking it down into manageable steps and using a clear, efficient approach. Remember, this type of problem is an excellent way to practice applying greedy algorithms with constraints. If you found this helpful, please like and subscribe, and let's continue learning together. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!